Good morning, dear students. Today we will go through periodic classification and chemical bonding. To start with, periodic table synopsis. As we know, the periodic table, the modern periodic table, is constructed based on modern periodic law. The modern periodic law states that the physical and chemical properties of elements are periodic function of their atomic numbers. Earlier, the Mendeleev periodic law was based on atomic masses, and the modern periodic table is constructed based on atomic numbers. The present form of periodic table is also known as long form of periodic table, and as we know, there are 7 periods and 18 groups. These are classified, the elements are classified into 4 blocks based on their electronic configuration, that is S block elements, P block elements, D block elements and F block elements. So let us go through each one individually. What are exactly S block elements? So these are the elements in which the differentiating electron enters into S subshell of the outermost shell. The general electronic configuration is always ending with NS1 or NS2. So this will be mainly group 1 and group 2, that is alkali metals and alkaline earth metals. So these are highly reactive metals. So two groups constitute S block elements. P block elements, these are the elements in which the differentiating electron enters P subshell of the outermost shell. So the general configuration is NS2 and NP126. This block contain both metals, non-metals as well as metalloids. All 3 types of elements are present. There are 6 groups coming under this category, that is group 16 and group 18. Sorry. S block and P block elements together, they are known as representative elements. They do represent their principal quantum number because the electron is entering into the outermost shell, which represents the principal quantum number of the atom. D block elements are the elements in which the differentiating electron enters into D subshell of the penultimate shell, so one less than the outermost shell. So NS1 to 2 and N minus 1D 1 to 10. There is also known as transition elements because they form a transition kind of a state between S block elements and P block elements. That is, the properties of these elements lie exactly in between to that of S block and P block. That's why they are called as transition elements. F block elements, these are the elements in which the differentiating electron enters into F subshell of anti-penultimate shell, 2 less than the outermost shell. So general electronic configuration is NS2, N minus 1D can have 0 or 1 electron, and N minus 2F will have from 1 to 14 electrons. These are a part of transition element block, so these are also known as inner transition elements. This particular block has 2 types of element. One is called as lanthanides, other one is called as actinides, and this block is separately placed at the bottom of the periodic table. Periodic properties. The properties of elements which show a regular variation when we move in the increasing order of atomic numbers, or these properties will show regular repetition after regular intervals when we arrange the elements in increasing order of atomic numbers. So some of the properties which are important periodic properties are atomic radius, ionization energy, electron gain enthalpy and electronegativity. So let us see one by one. Atomic radius. The atomic radius is actually defined as the distance between the nucleus and the outermost electron of an isolated gaseous atom. But if I take an isolated atom, the electron density can go up to infinite distance from the nucleus. Theoretically, even at infinite distance, electron density will not become 0. So we cannot get the absolute value of atomic size if I take an isolated gaseous atom. So to understand atomic size, we have alternate means, that is covalent radius, van der Waals radius and ionic radius. What exactly is covalent radius? So if I take covalent radius, it is half the distance between nuclei of two atoms of same element bonded through a single covalent bond. So if I take for example, let us say this is one atom, this is the nucleus. So this is the second atom where electron cloud is partially overlapped. This is the bond length. So half of this distance is going to be covalent radius. So covalent radius is half the bond length of covalent bond between two atoms of same element. On the other hand, van der Waals radius, so it is half the distance between the two nuclei of atom of same elements which are non-bonded and belonging to adjacent molecules, and very importantly this distance to be measured in solid state, because in liquid and gaseous state the molecules will be in movement. The adjacent atoms of different molecules we cannot measure accurately, it keeps changing. As a result, van der Waals radius to be measured in solid state. Suppose I take the representation. So this is one molecule. So as we discussed now, this is bond length, and if I take the second molecule, it is not bonded, so it is not going to be in contact, electron cloud will not overlap. So this is also bond length, and this is the distance between the two nuclei, and half of this distance is van der Waals radius. So generally you can see very clearly in the previous thing, this is the covalent radius, which is half of bond length where electron clouds are partially merged, and here the electron clouds are separated. There is a small distance separating the two atoms. So van der Waals radius obviously greater compared to covalent radius because it is non-bonded atoms. Ionic radius. So ionic radius is the distance from the center of the ion and a point up to which there is an influence of its electron cloud. So generally in ionic compounds, the distance between the two nuclei will be sum of the ionic radii of cation and anion. So if you take cation, cation is formed by loss of an electron, so electron cloud gets shrinked, and anion is formed by adding one electron, so electron cloud expands. As a result, the size of cation is always lesser than the neutral atom, size of anion is always greater than the neutral atom size. How do atomic size varies across a period and down the group? So generally atomic size decreases across a period and increases down the group. So the 2 points which are defining the atomic size would be the effective nuclear charge and the shielding effect. So across the period, if I take, the electrons are at the same main energy level. So the screening effect is not going to increase considerably, but effective nuclear charge increases considerably. As a result, the atomic size decreases. Down the group, if you go, the electrons are added to next and next higher energy levels or energy shells. So for one atom to other atom, extra shell of electrons are added. So shielding effect predominantly increases compared to nuclear charge. So as a result, the atomic size decreases. Ionization energy. Ionization energy is the energy required to remove the outermost electron, from an isolated gaseous atom. So it is always endothermic. Then successive ionization energy is always increases. So if I take one atom, neutral atom, remove one electron, you get a cation. Atomic size decreases. So it is difficult to remove an electron from a positively charged atom, positively charged ion, than the neutral atom. So second ionization energy of an atom always greater than the first ionization energy, and third ionization energy is always greater than the second IE value. So IE1 less than IE2 less than IE3. How does ionization energy varies across a period and down the group? So it will generally increases across the period and decreases down the group. So again it depends upon the atomic size. Atomic size decreases across the period, size is lesser, the outermost electron is held firmly by the nucleus, so the ionization energy will be high. So smaller the atom, higher is the ionization energy. And one more important point here, it depends on electronic configuration. So generally the half filled and completely filled atomic orbitals will have extra stability. So these elements will have higher ionization energy than the expected value. So elements in group 2, group 15 and group 18 will have high ionization energy values because of half filled and completely filled subshells. Electron gain enthalpy. Electron gain enthalpy is opposite of ionization energy. So it is the amount of energy released when electrons are added to the outermost shell of an isolated gaseous atom. In ionization energy, we remove the electron. In electron gain enthalpy, we add an electron. So amount of energy released when electron is added to outermost shell of isolated gaseous atom is called as electron gain enthalpy. For most of the elements, the first electron gain enthalpy is negative, means it is exothermic process. Heat will be liberated. But the second electron gain enthalpy, so once we add one electron, it becomes an anion. To add one more electron to the anion, always it is going to be endothermic process. We have to supply energy because it cannot easily accept the second electron, because already the nucleus is having more number of electrons to hold on to. As a result, it becomes an endothermic process. How does electron gain enthalpy changes in a period and on the group? Again, it depends upon the size. So electron gain enthalpy increases across the period and decreases down the group. So smaller the size of the atom, extra electron can be held by nucleus more firmly, because the distance between the nucleus and the electron will be less. So amount of energy released will be higher. If the atoms are going to be bigger, then electron cannot be held firmly by the nucleus. So as the size of atom decreases, electron gain enthalpy increases. Then half filled and completely filled subshells, they have already attained extra stability. They won't readily accept one extra electron. So electron gain enthalpy of these elements will be much lesser. Then noble gases will be always highly endothermic, very difficult to add one extra electron to the outermost shell of or the to the noble gas, because already outermost shell is completely filled. So generally, if I take the across a period, electron gain enthalpy increases. So it is maximum for halogens. So halogen require only one electron to attain that octet state. So electron gain enthalpy of halogen will be maximum, and they need one electron to attain the stability. So among halogen, the electron gain enthalpy decreases down the group. But one exception, chlorine has a higher electron gain enthalpy than fluorine, because fluorine is a small in size. So addition of one more electron introduces more of interelectronic repulsion that will slightly destabilize the ion. As a result, the amount of heat liberated, no doubt in both fluorine and chlorine, heat will be liberated. The amount of heat liberated when we add an electron is less in case of fluorine compared to chlorine. So the order will be chlorine, fluorine, bromine and iodine. Then electronegativity. Electronegativity is the ability of an atom to attract a shared electron pair towards itself. So electronegativity is a property of an atom in a molecule. So far whatever we discussed, they are all absolute property of an atom, but here the electronegativity is property of an atom whenever it is bonded to another atom. So electronegativity generally increases across a period and decreases down the group, because that also depends upon the size of the atom. And in case of electronegativity, fluorine is the most electronegative element in the periodic table, and oxygen is the second most electronegative element. So these two are the highly electronegative elements in case of halogens and oxygen. How to measure electronegativity? There are three different types of scales are available. One is called as Pauling scale, and second one is Mulliken scale, and finally Aldrich scale. So Pauling scale is the most widely used electronegativity scale, but the Mulliken scale values are 2.8 times higher than the Pauling scale of electronegativity. If you want to convert the Mulliken scale to Pauling scale, you have to divide by 2.8. Electropositivity. Electropositivity is the ability of an atom to lose the outermost electron and convert into cation. So it is almost related to ionization energy. So it is also termed as metallic character. And electropositivity is opposite of electronegativity. So electropositivity decreases across a period and increases down the group. As we go down the group, the non-metallic character will convert into metallic character. The ability of the atom to lose electron increases as we go down the group. Melting and boiling points. So melting and boiling points increases from left to right, reaches a maximum in the carbon group and then drastically decreases because the physical state of the element and the nature of bonding will change. So towards the beginning we have metals and towards the end right side we have non-metals, gases are present. So melting point and boiling point will gradually increase, reaches maximum in the carbon group and then decreases. Down the group, if I take melting and boiling point show regular trend, either they increase or either they are going to decrease, but the variation is not same in all the group. If I take alkali metals, in alkali metals the melting point decreases down the group, whereas in case of halogen the melting point and boiling point increases down the group. So that is for periodic classification and periodic properties. Now we will move on to chemical bond. Chemical bond is the force of attraction which holds atoms together in a molecule. Precisely, we can define chemical bond as force of attraction which holds the atoms or molecules or ions together in the molecule. And atoms enter into bond formation in order to attain the stability. So they can enter into bond formation either by mutual sharing of electron or by transference of electron. All this will happen only to attain stability. So different types of chemical bond. So we know ionic or electrovalent bond, then covalent bond, coordinate covalent bond, hydrogen bond, metallic bond and intermolecular forces. These are the different types of attractive force existing between the atoms in a molecule. We will take one by one. Ionic or electrovalent bond. Ionic bond is formed due to the complete transfer of one or more than one electron from an electropositive atom to an electronegative atom. So the number of electron transferred is known as electrovalency. So ionic bond is due to the complete transference of one electron or more than one electron always from an electropositive atom to an electronegative atom. What are the factors which favors ionic bond formation? So first one, the cation formation should be easier, the anion formation should be easier, the attractive forces should be holding them together. So low ionization energy of cation forming atom. If ionization energy is less, it can easily convert into cation. Then high electron gain enthalpy or electron affinity of anion forming atom, because more the electron gain enthalpy in terms of negative value, that means it can absorb one electron more easily to convert into stable anion. And larger difference between the electronegativity of the two atoms. So higher the electronegative difference, then the bond formation is going to be predominantly ionic compared to covalent nature. Then very important is lattice energy, that should be high. So what exactly is this lattice energy? Lattice energy is the amount of energy released when 1 mole of the crystal, solid crystal, formed from its constituent gaseous ions. So ions are already in the gaseous phase, they are combining to form the solid form, and that amount of energy released will be called as lattice energy. And lattice energy cannot be determined experimentally. So we can never determine experimentally the value of lattice energy. So we theoretically calculate using the concept of Born-Haber cycle. So what exactly is Born-Haber cycle? So Born-Haber cycle is based on what is called as Hess law of constant heat summation. So Hess law of constant heat summation says that during a chemical reaction, the amount of heat liberated or absorbed will remain same. The enthalpy change of a reaction will remain same whether the reaction is carried out in one step or in multiple steps. So let us see bond neighbor cycle of simple example NaCl. So sodium solid when combined with half Cl2 gives NaCl solid. So this is nothing but the enthalpy of formation. So direct conversion, sodium 1 mole reacts with half mole of chlorine to form sodium chloride solid. The amount of energy released will be taken as delta H formation. Theoretically, I can say the steps involved in conversion of this. See, sodium in case of solid state, it has to convert into gaseous phase. That means the enthalpy of sublimation is involved. So sodium solid is becoming sodium gas. Then sodium gas, you have to supply IE1 value to remove one electron, so become Na plus. So this is a summation of delta H sublimation and IE1 value. Same way chlorine molecules, you have to break all the bonds between chlorine molecule. So half of bond dissociation is you have to submit. So it becomes chlorine atoms in gaseous phase, and then add one electron, amount of energy released nothing but electron affinity value to convert into Cl minus. Then these two will combine to form NaCl. So the amount of energy is nothing but lattice energy, that is U. So if I take Hess law of constant heat summation, this delta HF should be equal to delta HS plus IE1 plus half of delta H dissociation plus EA value plus U. So I can find out U because I know all the other values. This is how we theoretically calculate lattice energy of any crystalline substance. Properties of ionic compounds. So they are crystalline solids at room temperature. They have very high boiling and melting points. Since they are ionic, they are soluble in polar solvents like water and insoluble in non-polar solvents like benzene. They conduct electricity either in solution or in molten state. Going to covalent bond. Covalent bond is a bond formed due to mutual sharing of one or more than one electron pair between two atoms. And number of electron pairs shared is known as covalency of the molecule or atom. So covalent bond is always formed due to mutual sharing of electron pairs between the two atoms. If one electron pair is shared, it is going to form single bond. If two electron pairs are shared, it is going to form double bond. Three electron pairs are shared, forms triple bond. What are the properties of covalent compounds? So unlike ionic compounds, they also exist as solids, liquids and also gaseous at room temperature. And comparatively, they have much lower boiling and melting points. Since they are existing as molecules, they are not ionizing, so they are insoluble in polar solvents but soluble in non-polar solvents like benzene, toluene, etc. But note that some of the covalent compound are also soluble in water. In that case, the reason is mainly hydrogen bonding. So unlike ionic compounds, they are bad conductors of electricity either in solution or in their pure form. They won't conduct electricity. So there are various theories put forward to explain the covalent bond formation. The first and foremost theory is Lewis theory. In this Lewis theory, the only reason considered was the atoms enter into bond formation to attain the stable octet configuration. The only driving force for the atom to share electron pair between other atoms is to attain the octet state, that is NS2 NP6 configuration, which is ultimately stable configuration. But this theory fails to explain bonding in some of the molecules, like some molecules may have less than 8 electrons in the outermost shell but still the molecule is stable, and we have even superoctets like more than 8 electrons in the outermost shell but still they are stable. So BF3 is called as Lewis acid, which is going to be having only 6 electrons in the outermost shell of boron, still the molecule is quite stable. And PCl5, SF6 are the molecules where phosphorus has 10 electrons, sulfur has 12 electrons around the central in their outermost shell, but still the molecules are quite highly stable. So this concept could not be explained by Lewis theory. The most successful theory for covalent bond formation is valence bond theory. According to valence bond theory, the covalent bond is formed due to overlapping of atomic orbitals. It is a extension of wave mechanical model of an atom. So wave functions, whatever we discussed in atomic structure, was used, and that wave mechanical concept is extended to explain bonding, which is nothing but coming in the form of valence bond theory. So the atomic orbitals will overlap with each other to form a bond. Based on the type of overlapping, we have two types of bond. One is sigma bond, another one is pi bond. So sigma bond is formed when atomic orbitals overlap along the axis. So axial overlapping or direct overlapping will always form sigma bond. If the atomic orbitals overlap laterally or sidewise, the bond formed will be pi bond. Since in case of lateral overlapping, the extent of overlapping is not very high, the pi bond is always weaker than sigma bond. In a multiple bond, only one sigma bond exists, other bonds has to be pi bonds. So in a double bond, there is one sigma and one pi. In triple bond, there is one sigma and two pi bonds. To explain the bonding in various other molecules, the concept of hybridization is introduced by valence bond theory. So in this hybridization, it is a phenomena where the atomic orbitals of the outermost shell of the central atom undergo mixing to form equal number of new orbitals called as hybrid orbitals, and these hybrid orbitals will have same energy, shape and size but have different orientation in three-dimensional space. Before combination, the atomic orbitals are going to be of same energy or it can be of comparable energy, but once they mix and form hybrid orbitals, they are all going to have equal energy, same kind of shape but different orientation. And always the number of atomic orbitals overlapping will be equal to number of hybrid orbitals formed in the atom. And based on the orientation, a definite geometrical shape will be given for each and every hybridization. So covalent bonds are directional in space. As a result, here also hybrid orbitals also directional in space, giving a regular geometry for the molecule. So let us take one by one sp3 hybridization. So in this case, as we know, one s orbital and three p orbitals are involved in hybridization. The four hybrid orbitals are directed towards corners of a regular tetrahedron. So sp3 hybridization is also called as tetrahedron hybridization. And in this case, the bond angle is exactly equal to 109 degree 28 minutes. So methane, CCl4 are the examples of sp3 hybrid molecules. So carbon in methane, carbon in CCl4 undergo sp3 hybridization to form four bonds with hydrogen or chlorine. sp2 hybridization, as the name itself says, it has one s and two p orbitals involved in hybridization. So total number of orbitals will be 3, and these 3 orbitals are directed in one plane in the form of a trigonal planar structure. So trigonal planar structure means this is the central atom. You have 1, 2, 3. This will be 120 degree. So bond angle is 120 degree. Example is BCl3, BF3, and ethene, the alkene, the sp2 hybrid carbon, double bonded carbon atom will be sp2 hybrid. So ethene is also one example for sp2 hybridization. sp hybridization, the name itself says, one s and one p orbital involved in hybridization. Only two orbitals, the best possible orientation is opposite to each other. So this is a central atom. So it is going to be one orbital like this, one orbital like this. The bond angle is 180 degrees. So bond angle is 180. The example is beryllium chloride, and also alkynes. The triple bonded carbon in all alkynes will be sp hybridized. When d orbitals are involved in hybridization, sp3d hybridization, 1s, 3p, and among d subshell it is dz square orbital involved in sp3d hybridization. So the sp3d hybridization means there are 5 orbitals. So this is central atom. So 5 orbitals means there will be 1, 2, 3 trigonal planar, and perpendicular to that there will be 2 more. So this is going to be trigonal bipyramidal. like this trigonal bipyramid structure. So along the trigonal plane bond angle is 120 and among the perpendicular one bond angle is 90 degrees. So there are two types of bond angle, 120 degree and 90 degree. Example is PCl 5. sp3d2, in this one s orbital, 3 p orbital and dz square and dx squared minus y square are involved in sp3d2 hybridization. There are 6 hybrid orbital which are directed along corners of regular octahedron. So that means there is a square plane kind of a structure. This is central atom. So 1, 2, 3, 4 and perpendicular to each other. So there are 6 corners of octahedron. All the bond angles are exactly equal to 90. It is one of the perfectly symmetrical orientation. Example is sulfur hexafluoride. sp3d3. So in case of this 1s, 1, 3p and 3d, that is dxy, dyz, dzx are involved in hybridization. So these are oriented along pentagonal bipyramid. So pentagonal bipyramid structure like this. So central atom 1, 2, 3, 4, 5, 6 and 7. So the bond angle along the pentagon plane is 108 and the perpendicular ones are 90 degrees. Example is IF7. How to find the hybridization of an atom in the molecule? So we can go over a simple formula. You have to find a number x. So x is equal to total number of valence electron of the central atom and surrounding it how many number of monovalent atoms are present. And if the ion is a cation, you have to minus the charge of cation. If the ion is an anion, you have to add the charge on anion. So by this you get x as number. X can be 2, 3, 4, 5, 6, 7. If x is 2, it is sp, x is 3, sp2, x is 4, sp3, x is 5, sp3d, 6, it is sp3d2 and 7, it is sp3d3. So find the number x, then map for corresponding hybridization. So I will repeat, x is equal to number of valence electron in the central atom plus the number of monovalent atom bonded to it minus the charge of cation and plus the charge of the anion. If the molecule given is neither a cation nor anion, the last two parameters will not be there. VSEPR theory, one more theory which will explain the basic geometry of molecule. So the geometry of the molecule depends mainly on the number of electron pairs around the central atom. So geometry depends only on the number of electron pair on the central atom, not on the terminal atoms. These electron pairs in the central atom tend to orient themselves in 3D space to have a minimum repulsions and maximum stability. So the orientation of this electron pair will be in such a way that the repulsion between these electron pairs are minimum. So there are two types of electron pairs. One can be bonded pair, other can be lone pair. Since lone pair is controlled by only one atom, it occupies larger space in 3D. As a result, lone pair, bond pair repulsions are going to be different. So order of repulsions are lone pair will be highest repulsive force, then it is lone pair, bond pair and finally bond pair repulsion. So let us see how the geometry can be explained. So first I will take molecule AB. So AB means two atoms bonded to each other with one bond pair. So 2 bond pair, 0 lone pair. So central atom is going to be sp and linear. AB2. So this would be AB2 rather than AB. So AB2 means 2 bond pair, 0 lone pair. So it is linear. BeCl2 is the example. This is AB3. So AB3 will have 3 bond pairs and 0 lone pair, sp2 hybridization, trigonal planar and BeCl3. This is the example. In one of the electron can be lone pair, so AB2E it is, not ABE, AB2E. So it's going to be 2 bond pair and 1 lone pair. So the geometry is always same as hybridization, but the shape can be different because lone pair cannot be identifying the shape of the molecule. So the geometry is still trigonal planar, but because one lone pair is there out of three becomes two invisible, it becomes bent. So NO2 minus is the example for this. Then AB4 means bond pairs are 4 and 0 lone pairs. The 4 pairs around the central atom means sp3 hybridization. The geometry will be tetrahedron. So since there are no lone pairs, it is also tetrahedron, and methane is the example. One electron pair is becoming lone pair, then 3 and 1. Still hybridization is sp3 because 4 pairs around the central atom. The geometry is still tetrahedron because one of the electron pair become lone pair. The shape will be pyramidal, and the example is ammonia. If is A, B, 2, E2, that means 2 bond pair, 2 lone pairs. Still there are 4 pairs, so sp3, tetrahedron is the geometry, and bent is the shape, and water is the example. AB5, 5 bond pair, 0 lone pair, so sp3d. Trigonal bipyramidal geometry is possible for 4 types of molecule. So one lone pair will make it geometry as seesaw, 2 lone pair will make the geometry as T shape, and 3 lone pair will make the geometry as linear. So shapes are different, geometry will remain same. So in all the cases the hybridization is sp3d. So example for all 5 bond pairs will be PCl5, 4 bond pair and 1 lone pair will be SF4, 3 bond pair, 2 lone pair will be ICl3, and 2 bond pair and 3 lone pair would be XeF2. So 4 shapes are possible for a molecule with central atom sp3d hybridized, that is trigonal bipyramid, seesaw, T-shape and linear. If it is AB6, you can say 6 bond pair, 0 lone pair, or 5 and 1 and 4 or 2. In all the 3 cases, sp3d2 is the hybridization, geometry is octahedron. So if there are no lone pair, shape is also octahedron. If there is one lone pair, it becomes square pyramid. If there are 2 lone pair, it becomes square planar. So examples are SF6 for 0 lone pair, XeOF4 for square pyramidal geometry, XeF4 for the square planar geometry. VSEPR theory, AB7, 7 bond pair, 0 lone pair, sp3d3, 6 and 1 also sp3d3. So both the cases sp3d3 geometry is pentagonal bipyramid, the shape is pentagonal bipyramid if there are no lone pairs, or distorted octahedron if there is one lone pair. Example is IF7 and XeF6. Moving to molecular orbital theory. The molecular orbital theory is a three-dimensional region around the nuclei of all the atoms of a molecule where there is maximum probability of finding an electron. These molecular orbitals are controlled by all the nuclei of all the atoms, so it is polycentric in nature. And how these molecular orbitals are formed? These are formed by the combination of atomic orbitals. Now, when we say atomic orbitals are combining, the number of molecular orbitals are formed is always equal to number of atomic orbitals undergoing combination. How many atomic orbitals are combined, same number of molecular orbitals will be formed. Out of the molecular orbitals formed, half of the molecular orbitals are called as bonding molecular orbitals, that is BMO, and the remaining half is known as anti-bonding molecular orbitals called as ABMO. So in bonding molecular orbitals, the energy is less than the atomic orbitals, which favor bond formation, and anti-bonding molecular orbitals will have higher energy than the atomic orbitals, which oppose for bond formation. So while filling the molecular orbitals, we have to follow all the 3 rules how we follow in atomic orbitals, that is Aufbau principle, Pauli's principle and Hund's rule. How actually the molecular orbitals are formed? There is a theory called as LCAO method. LCAO stands for linear combination of atomic orbitals. So as we know, atomic orbitals are represented by their wave function, that is psi. So these wave functions can be combined in a linear fashion, either in symmetrical way or unsymmetrical way. So symmetric combination or constructive combination will give always bonding molecular orbitals. So psi A plus psi B, A and B are 2 atoms which are forming a molecule, then wave function of A will be psi A, wave function of B will be psi B. If I add psi A and psi B, I get bonding molecular orbital, constructive overlapping. Asymmetric or destructive overlapping or combination will give ABMO, that is psi A minus psi B is equal to a wave function of anti-bonding molecular orbital. So, there is a linear combination of atomic orbital, one is additive overlap, other one is subtractive overlap. Basic difference between BMO and ABMO. So, a BMO formed by symmetric combination of atomic orbital, and in case of ABMO, asymmetric combination of atomic orbitals. And BMO has lower energy than the atomic orbitals, and here it is high energy than the atomic orbitals. It favors bond formation, it does not favor bond formation. Very important, the BMO may or may not have a nodal plane, but in case of ABMO, always it will have minimum of one nodal plane. Electron density is maximum between the two nuclei in case of bonding orbital. Electron density is minimum in case of anti-bonding orbitals. Because of that reason only, anti-bonding will not favor bond formation. Types of molecular orbital. Depending upon the types of overlapping, we can have two types of molecular orbital, that is sigma molecular orbital and pi molecular orbital. As we know, sigma bond and pi bond more or less same. Sigma molecular orbitals are formed by axial overlapping of atomic orbitals to form the molecular orbitals. These may or may not have a nodal plane. Pi molecular orbitals, this is formed by lateral overlapping of atomic orbitals, and these will be having minimum of one nodal plane. So, we will see how the orbitals are formed. So, if I take s orbitals overlapping, constructive and destructive. So, if it is bonding, it is called as sigma 1s. If it is anti-bonding, it is called as sigma star 1s. So, you can see clearly the first one is constructive overlapping. The electron density between the two nuclei is maximum. As a result, this is bonding, that is sigma 1s, and you can see a nodal plane, it is going to be anti-bonding sigma star 1s. This plus and minus in the figure indicate the sign of the wave function. It is nothing to do with physical significance of the electron cloud or anything, it is just a sign of the wave function. If I take p orbital, so these are two lobes of p orbital, so this is overlapping along the axis. So, if I take the yellow one is overlapping with yellow one, they merge, that is constructive overlapping. So, electron density is maximum between the two nuclei, this is sigma 2pz, and if you take the yellow one is overlapping with blue one, it is destructive overlapping, they won't merge easily. So, there is a small gap between them, there is a nodal plane. So, electron density is minimum between the two nuclei, this is sigma star 2pz. Same way pi orbitals, so they are lateral overlapping. So, you can see yellow one is overlapping with yellow one, becomes a yellow lobe and bottom blue lobe. So, this is pi molecular orbitals pi 2px. So, here you can see in this particular yellow one and blue one and yellow one. So, if it is plus, this is minus, this is minus, this is plus. So, if yellow is, if I say it is plus, plus, minus, minus. So, this will be plus, this will be minus. Here also plus, minus, but overlapping is plus, minus, minus, plus. So, this is anti-bonding pi star 2px. Energy level diagram of molecular orbitals. You can see very clearly there are two types of energy level diagram for homonuclear diatomic molecules. First one is still up to nitrogen. This is up to nitrogen, this is after oxygen onwards. So, here sigma 1s, sigma star 1s is not shown, 2s is forming sigma 2s, sigma star 2s, then very important difference is here. So, in case of molecules up to 14 electrons in the system, the pi 2px and pi 2py orbitals will have lower energy than sigma 2pz orbital. If the number of electrons in the system crosses 14, then we have to follow this diagram where sigma 2pz is lesser in energy than pi 2px and pi 2py. So, these are the two diagrams we have to follow depending upon whether the number of electron is less than 14 or more than 14. Bond order is equal to half of number of electrons in bonding minus number of electrons in anti-bonding. So if the bond order is higher, the molecule will be relatively stable. If I say bond order is 0, then there is no bond formed between the two atoms, the molecule does not exist. So hydrogen molecule, as we know, hydrogen there is 1s electron and 1s electron, two hydrogen atoms, 1s electron. So total number of electron system is 2. So two atomic orbitals overlap to form two molecular orbitals, sigma 1s, sigma star 1s. Only two electrons, both electron goes to sigma 1s because I have to follow Aufbau principle. So number of electrons in bonding is 2, number of anti-bonding electrons are 0. So bond order is half of 2 minus 0, which is equal to 1. That means there is a single bond between two hydrogen atoms. Since there is no unpaired electrons in the molecular orbital, molecular magnetic property will be diamagnetic. If I take helium, He2 molecule, assuming that is existing, helium will be 1s2 configuration. There are two atoms of 1s2 configuration. So 2 plus 2, 4 electrons, sigma 1s, sigma star 1s. So you get 2 electrons to sigma 1s, 2 electrons to sigma star 1s. So the bond order will become 0. So there is no molecule of He2 exist. Say a nitrogen molecule, nitrogen 14 electrons. So 1s, sigma 1s, sigma star 1s is 4 electrons, that is already taken into consideration. Then remaining 10 electrons. So 2 electrons in 2s, here 2 electrons in 2s, so 4, sigma 2s, 2p, so sigma 2s will have 2 electrons, sigma star 2s will have 2 electrons, and 3 plus 3, 6 electrons in the 2p subshell of each of the nitrogen. Total 6 electrons I have to fill now. So pi 2px will take 2, pi 2py will take 2, and sigma 2pz will take 2. So there are 6 electrons in bonding, no electrons in anti-bonding, bond order becomes equal to 3. And there is no unpaired electron, nitrogen is diamagnetic in nature. The major drawback of valence bond theory was it is unable to explain the paramagnetic nature of oxygen. That was explained by MOT. So in case of oxygen, similarly, so it is more than 14 electrons. We have to follow second diagram. Sigma 2pz is lower energy and pi 2px, pi 2py will be high energy. So if you fill the electrons, you get two unpaired electrons in the anti-bonding orbitals. So bond order is 2. Because of two unpaired electron, magnetic property become paramagnetic. So MOT successfully explains the paramagnetic behavior of oxygen molecule. Moving to polar covalent bond. If the covalent bond formed between two atoms of different electronegativity, then electron pair is unequally shared. If there is unequal sharing of electron, the bond is known as polar covalent bond. If the electron pair shared equally, if the electronegativity is same for two atoms, the bond will be always non-polar covalent bond. So in polar molecule, there is a property called as dipole moment. So dipole moment is the product of magnitude of the positive or negative charge, product of the magnitude of partial positive or negative charge on the atom and the bond length. So mu is given by E into D. A polar molecule will have a permanent dipole moment and a non-polar molecule will have zero dipole moment. So the dipole moment measurement will be useful to find out whether the molecule is polar or non-polar. If it is diatomic molecule, usually we can find out E into D. If it is a polyatomic molecule, for each of the polar bond, we have to find the bond moments and take the vectorial resultant of all these bond moments. So for a polyatomic molecule, the net dipole moment is the resultant of all the individual bond moments. In a symmetrical molecule, net dipole moment becomes 0. Even though there are polar bonds, the molecule being symmetrical, it will cancel out in terms of bond moments. If I take an example of carbon dioxide, so carbon dioxide structure is this. This is the polar bond moment is towards this direction, and this is going to be in the opposite direction. So mu will be equal to 0. And a non-symmetrical molecule definitely will have non-zero dipole moment. So dipole moment measurements can also be used to predict the geometry of the molecules. Polarization. So it is a phenomena where when a cation comes near to anion, the cation will try to distort the electron cloud of anion. The distortion of anionic electron cloud by the cation is called as polarization. So when the polarization is maximum, so the cation charge is high and size is very small. Charge density will be very high on the cation, so it can attract the electron cloud of anion very strongly. So if the anion electron cloud is attracted very strongly towards cation, the electron density between the two nuclei will increase. As a result, it introduces covalent character to the ionic compound. So degree of covalency increases with the increase in polarization. So this is governed by Fajan rule. This is summarized as Fajan rule. In case of cation being smaller and charge being higher, greater will be its polarizing power. It is able to distort the electron cloud of anion very effectively. If the anion is larger, it can get distorted very easily. If the anion is smaller, it will not allow the cation to take the electron cloud easily. If the anion is larger, the nucleus is having less control over the outermost electron cloud, so cation can distort the electron cloud easily. So smaller the cation and larger the anion, polarization is maximum, that will have higher covalent character. So this is nothing but Fajan rule. Small cation and large anion of the compound, the covalent character will be more. So larger cation and smaller anion, the ionic character is going to be more. So if you are given with 4 different molecules, to find out the degree of covalency or ionic character, you have to go with the size of the cation and size of anion. Coordinate covalent bond. It is also covalent bond. The only difference between covalent and coordinate bond is the electron pair which is shared is coming from only one atom. So covalent bond found between two atoms in which shared electron pair is coming only from one of the bonded atom is called as coordinate covalent bond. A coordinate covalent bond is relatively more stronger than covalent bond. Hydrogen bond. This is a very important type of bond, very weak but plays a significant role. So attraction between the hydrogen atom which is bonded to highly electronegative atom like oxygen, fluorine, nitrogen, and the highly electronegative atom of a different molecule or within the same molecule. So hydrogen atom which is bonded to these three, F, O and N. Then this hydrogen attracted by other electronegative atom, that is also F, O and N. These can be present in different molecule or within the same molecule. So based on the bonding within the molecule or outside the molecule, we have two types of hydrogen bonding. One is intermolecular hydrogen bonding, second one is intramolecular hydrogen bonding. If I take intermolecular hydrogen bonding, the hydrogen bond formation is between two different molecules. So if I take H2O here, you can see very clearly oxygen is more electronegative atom. So here hydrogen is bonded to this oxygen by covalent bond, and this dotted line what we can see is hydrogen bond. So the two water molecules are joining together through hydrogen bond. So because of this association of molecules, the consequence will be the boiling point will be elevated. So in case of intramolecular, you can see very clearly it's a phenol, orthonitrophenol. OH bond is there. This is H bonded to oxygen through sigma bond, and nitro group is also having one oxygen which is in the same molecule. These are held by hydrogen bond. So intramolecular hydrogen bonding within the molecule. What are the consequences of hydrogen bonding? So very important, intermolecular hydrogen bonding increase the boiling point, intramolecular hydrogen bonding decrease the boiling point. And because of intermolecular hydrogen bonding, water exists as a liquid at room temperature due to hydrogen bonding. And also water has maximum density at 4 degrees Celsius. There is an expansion instead of contraction when the water is cooled from 4 degree to 0 degree, which is called as anomalous expansion. To convert into solid form, hydrogen bond is of a higher length compared to covalent bond. So water molecule go away from each other and then they are going to set themselves at particular place where ice structure is obtained. So from 4 degree to 0 degree, there is expansion instead of contraction. And ice have less density than water, so it will float on water. Metallic bonding is a force of attraction which holds metal ions or kernels and free electrons in the metal crystal. This bonding in metal explained by a model called as electron C model, electron gas model. So this is the metal kernels. You can see here metal kernels. and these are the freely moving electrons. So the metal kernels are kept immersed in a sea of freely moving electron. That is the concept of electron sea model. So electron sea model can explain the properties, lustrous nature. So when light falls on the metal surface, the free electrons are set into oscillation, so it absorbs energy and re-emit the same. As a result, the metal surface appear lustrous in nature. Conductivity. So the free electrons are responsible for carrying electricity from one part of the metal crystal to other part of the metal crystal. So both thermal and electrical conductivity can be explained by presence of lots of free electrons. Thermoionic emission. When the metals are heated to a high temperature, the electrons will gain sufficient kinetic energy to escape out of the attractive forces. As a result, the kinetic energy of electron increases, and at a particular temperature the electron get emitted out of the metal surface. As a result, the thermoionic emission is observed. Then photoelectric effect. When light radiation falls on metals like cesium or rubidium, which have very low ionization energy, the energy of the light itself is sufficient to overcome the attractive forces. So that's going to eject the electrons out of the crystal. So both photoelectric effect and thermoionic emission can be explained by same electron sea model. Then finally, malleability and ductility. So in malleability, ductility means metals can be converted into thin sheets and thin wires. So when the metal is subjected to mechanical force, the layers of metal kernels will slide one over the other. The thickness of the metal can be decreased. It can be converted into thin sheets and thin wires. But remember, during this process, the three-dimensional arrangement of metal kernels with respect to each other will not be altered. The 3D structure of crystal structure of metals will not be altered, but it is only just defragmented to different thickness and to form thin wires and thin sheets. So these are the synopsis points in periodic table and chemical bonding. Thank you.
Welcome to Deeksha Online. Today we are going to discuss few important points related to S block. The S block elements. Group 1 and group 2 elements are called S block elements, and group 1 elements are lithium, sodium, potassium, rubidium, cesium, francium, and group 2 elements are beryllium, magnesium, calcium, strontium, barium, and radium. So group 1 and group 2 elements together are called S block elements. Let us take the first property, atomic size. The first group elements have largest atoms in each period. That is, across a period, atomic size will be decreasing. Therefore, the first atoms, means the first group atoms, will be having largest atomic size. And the size of the atom increases down the group. That is because down the group, number of orbits will be increasing. This is same with respect to second group also. In second group also, the atomic size will be increasing down the group. Then comes second property, density. So as we know, density depends upon two factors, mass as well as the volume. Means density is given by the mass and the volume here now. It is found that density increases down the group. That is because when you are moving down the group here, we can see more increase of mass when compared to increase of atomic volume. So this means down the group, the increase of mass is more when compared to increase of volume. So because of relative increase of mass more than that of the volume, density is increasing down the group. And exception is potassium. Potassium is found to be less dense than that of the sodium. It's found to be less dense than that of the sodium. That is because relatively potassium has higher atomic volume. Relatively, potassium has higher atomic volume. That is, potassium has more atomic volume than it should have. It is having more atomic volume than it should have. Therefore, density of potassium is less. So, order of densities will be lithium less than sodium and sodium is more than potassium. Then comes potassium less than rubidium and then cesium we have. And coming towards lithium, sodium, potassium are lighter elements. They are lighter than water. Implies the density is less than that of water. This is regarding density. Then second group elements. Second group elements are more dense and density once again increases down the group. Second group elements are more dense because of two things. They have smaller size, as well as larger mass. Implies their mass is more and volume is less, and thereby density of second group elements is more than that of density of the first group elements. Then coming towards property ionization potential. The first group elements have least ionization potential in that particular period. That is because of largest atomic size in that period. So first group elements have least value. And ionization potential will be decreasing down the group. That is because of increase in the atomic size down the group. All the elements of the first group exhibit +1 oxidation state. And in +1 oxidation state, the compounds are colorless. As well as diamagnetic in nature. And compounds such as potassium permanganate, KMnO4, potassium dichromate, potassium chromate, they are colored. The color is because of the anions which are present in that. Otherwise, the compounds of first group elements are colorless and diamagnetic in nature. Rubidium and cesium can lose electrons very much easily when exposed to visible light also. Because of larger size, they can lose electrons very much easily, and therefore they are used in the construction of photoelectric cells. So lithium and cesium can lose electrons very easily when exposed to visible light itself, and therefore they are used in the construction of photoelectric cells. When it comes to second group elements have higher IP values than that of the first group elements there. These higher IP values, because of small size, they have a smaller size, as well as they will be having stable NS2 configuration. Because of stable configuration and smaller size, they are having higher IP values when compared to group 1 elements. And uniformly, all of them will be exhibiting +2 oxidation state. So group 1 +1 state we have, group 2 they are exhibiting +2 oxidation state. This is regarding ionization potential. When it comes to electropositive character, alkali metals are highly electropositive in nature because of larger size, and then metallic property depends upon electropositivity. Since they have more electropositive character, they are more metallic in nature. So alkali metals are highly electropositive and highly metallic in nature. And metallic property, the metallic nature is decreasing, metallic nature is increasing down the group. That is because down the group we are observing down the group electropositive nature is increasing, thereby metallic nature also increases down the group. When it comes to second group elements are lesser metallic in nature because they have lesser electropositivity. But again, down the group, metallic nature will be increasing there as regarding second group, electropositive character. Then melting points and boiling points. Melting points and boiling points depend upon metallic bond strength. Means higher metallic bond strength, higher melting points. Metallic bond strength in turn depends upon the size of the atom and number of valence electrons involving in bonding. Metallic bond strength depends upon size of the atom as well as number of valence electrons involving in bonding. Means if size is larger, they are going to have lesser melting point. Valence electrons are more, they are going to have higher melting point. And in this case, they have lesser metallic bond strength, and the metallic bond strength is decreasing down the group. Because of larger size, they have lesser metallic bond strength, and metallic bond strength is decreasing down the group, and therefore melting and boiling points are decreasing down the group. Melting and boiling points decrease down the group because of decreasing in the metallic bond strength, and they are very soft metals and can be cut even with a knife also. Soft metals and we can cut with knife. Then when it comes to second group elements, they are having stronger metallic bond. because from second group elements they're smaller in size and we have more number of valence electrons, therefore they have a stronger metallic bond. That is because of smaller size as well as more number of valence electrons. But when it comes to the trend, from second group onwards there is no trend in melting point, because melting point also depends on crystal structure of these elements. Melting points also depends upon crystal structure, and here all the elements have different crystalline structures, and therefore melting points do not vary uniformly. But what we need to remember is highest melting point is for beryllium and lowest melting point is for magnesium. High for beryllium, low for magnesium we have. So melting points are also depending upon the crystalline structures. These elements, all the elements have different crystalline structures, hence there is no uniform melting point. There is no order in the melting points. But we have to remember beryllium is highest and magnesium is the least. Then comes hydration. Then comes the hydration property. The metal ions undergo hydration in water and form hydrated ions. And the hydrated ion formation depends upon the positive charge density. Lithium being smaller in size, it is having greater positive charge and therefore undergoes hydration to a greater extent. Since Li plus has a greater positive charge density, it undergoes hydration to a greater extent. And then its hydrated ion size also will be larger because of more hydration there now. Now when you compare the size of hydrated ions in this group, here down the group the size is getting reduced because cesium cannot undergo hydration heavily as lithium undergoes hydration heavily there now. That is regarding the order of hydration we have. Then when it comes to the extent of hydration, there is also decreasing down the group because down the group positive charge density is decreasing. Suppose when you take the order of the size of these ions, including water molecule, that comes like this. So lithium, say H2O, say taken X times, say positive here, no, plus ion, will be greater than that of sodium ion, then that of. Finally, you are going to get here cesium H2O, say taken X times here. This is the order of the hydrated ions we have. So lithium is going to have very much larger size, and last one cesium is going to have smaller size. It's depending upon the positive charge density. More positive charge density, heavy hydration. Then comes ionic mobility. Ionic mobility depends upon the size of the ion in water. So the size is small, it can move very much fastly. Larger size ion cannot move fastly. So ionic mobility depends upon the size of the ion. So ionic mobility of these ions in water is increasing down the group, because you have seen that the size of the ions, these things are decreasing. So lithium ion size with water molecule is very much bigger, and therefore this ion cannot move very much faster. That is, its hydrated ion size is larger here, and cesium ion including water molecule is very much small, and therefore cesium ion can move very much fastly. So increasing order of ionic mobilities will be in this order we have. So depends upon hydration. So heavily hydrated ion cannot move fastly, and less hydration means ion can move fastly. Therefore lithium cannot move fastly, whereas cesium ion can move fastly. Then second group elements. Second group elements have higher hydration enthalpy because of more charge density. That is, they have a smaller size and they need to have larger charge also. So therefore they are going to have more charge density. And because of these hydration enthalpies only, the second group metal salts are existing as mainly hydrated salts. That is to say, for example, if you take magnesium chloride, it is existing as hexahydrate. Like say take calcium chloride, exists as hexahydrate there. So these salts are existing as hydrated salts because of their greater hydration enthalpy values. Then comes reducing property. So alkali metals are very good reducing agents because of, we can say, low ionization energies. They can lose electrons easily, and therefore they are very good reducing agents. And reducing property is increasing down the group. Reducing property increases down the group. And here the exception is lithium we have. Lithium is having higher reducing property. So lithium is strongest reducing agent, and that is because of its largest hydration energy. So alkali metals are good reducing agents, and reducing strength is increasing down the group, but only exception is lithium. Lithium is having higher reducing strength. That is because of its higher hydration enthalpy values. Let us see now the order. So to know the order, we need to construct a Born-Haber cycle which has three steps in that. Lithium solid, first of all sublimation, changing into gas, then comes ionization to ion, then going towards hydration property we have. So this step, the sublimation step, is going to be endothermic step. Means this as say delta H1. This value is going to be a positive value. Ionization also, it is an endothermic step. So delta H2 is also a positive value we have now. And only this value delta H3 hydration will be a negative value for us now. And then the resultant depends upon the sum of all these energy values. Means delta H, the total delta H is given as delta H1 plus delta H2 plus delta H3 we have. Higher negative delta H indicates it is going to be a stronger reducing agent. So summation must be negative value. Higher negative value indicates that is going to be a stronger reducing agent. And then lithium is having higher value of hydration here. This value is very much higher for lithium, which is compensating both IP value as well as sublimation values. So therefore, this compensates both these two steps here and having higher negative value, and thereby lithium is having highest reducing strength we have. When you compare other elements, we can even replace these lithium by metal in general and construct a Born-Haber cycle, and we can know relatively which is stronger reducing agent. When it comes to second group elements, they have lesser reducing strength. Lesser reducing strength means here the total delta H value must be lesser negative when compared to first group elements. That is because of, you can say, higher sublimation as well as higher IP values. Because they are having smaller size and stable configuration, they are going to have stronger metallic bonding, hence they have higher sublimation, and because of stable configuration they are having higher IP values. Because of these two higher positive values here, they are going to have lesser negative delta H. That leads to lesser reducing strength. So second group elements have lesser reducing strength because of higher sublimation and then because of the higher IP values. Then comes the flame test. So these metal ions impart color to the flame. That is, reason behind is the energy of the flame is sufficient to excite the electrons of these metals. During de-excitation, means electrons are getting excited first, and during de-excitation of electrons, the energy liberated, means the radiation coming out from that, will fall within visible portion. Therefore, they impart color. After excitation and de-excitation takes place, during de-excitation of the electrons, the energy liberated in the form of radiation that falls within visible portion. Therefore, they impart color. And in the second group elements, except beryllium and magnesium, others are imparting color. That is because beryllium and magnesium elements are smaller in size and their electrons cannot be excited by the energy of the flame. When it comes to second group, only Be and Mg do not impart any color for the flame because of the smaller size and their electrons cannot be excited by the flame. So the colors we need to remember: lithium, crimson red; sodium, golden yellow; potassium, lilac we have; rubidium and cesium, both are exhibiting violet color. And comes to second group elements, calcium, brick red; apple, barium, apple green; crimson comes to be strontium exhibits crimson red color in the flame we have. These are the flame tests we have. Then comes polarizing power. Polarizing power basically depends upon the charge as well as ionic size square. So if you have similar polarizing power, similar properties we have. If you have a greater polarizing power, then it is going to have a greater attraction for electronic cloud. So more polarizing power means more attraction for electronic cloud. and that leads to more covalent character. So lithium Li plus is having more polarizing power, and therefore it forms mainly covalent compounds. Because of higher polarizing power of lithium compounds are covalent in nature. Other alkali metals form ionic compounds. So only lithium forms mainly, or lithium compounds have covalent character, whereas other alkali metals have only ionic property. Coming towards second group elements have higher polarizing power than that of even first group elements also, because they have smaller size as well as the smaller size, and then they have charge. They have more charge and small size they have, and thereby they are having more polarizing power, and therefore their compounds are much more covalent in nature. And in second group elements here, beryllium element the forms covalent compounds, whereas all others are forming ionic compounds. So in first group, lithium compounds have covalent character. In second group, beryllium forms covalent compounds, others being ionic in nature. This is regarding polarizing power and the nature of the bonds formed by these elements. Then comes solution in the liquid ammonia. These first group elements dissolve in liquid ammonia and form a deep blue color solution. So when you're dissolving the metals in the liquid ammonia, see the solution contains electrons in them. That is, we can see like this, a metal dissolving in ammonia, it ionizes, it forms metal ion, plus electrons are given by that. And the metal ions which are present, they take up ammonia molecules. They are surrounded by ammonia molecules. It forms metal, say NH3 taken X times. This is said to be ammoniated cation. Then electrons are also surrounded by ammonia molecules. Say I am writing here YNH3, giving rise to, and this is called ammoniated electrons. This is called ammoniated electrons. So when you take all together the solution, say metal plus X plus Y moles of ammonia, giving rise to, it will be M NH3 taken X times plus electron, so NH3 taken Y times now. So the solution mainly contains here ammoniated cations and ammoniated electrons are present now. So these ions are present in the liquid ammonia solution of metals now, and they are imparting color to the solution now. Here the solution contains ammoniated cations and ammoniated electrons are there. That is, these two are there in the solution now. And then the solution exhibit following property because of these two. The solution is paramagnetic in nature, it's the reducing nature we have, as well as conductivity, of course along with the color also. And then here the paramagnetic property, the first two properties are because of the, we can say, electrons present in them. That is because of, we can say, ammoniated electrons which are there in that. When it comes to the second, that is a conductivity, we can say that is because of the ions which are present in that. So all the properties are because of those ions which are there in that. Similarly, second group elements also dissolve in liquid ammonia and form blue color solution. A similar reaction can be written even for the second group elements also. So first and second group metals are dissolving in liquid ammonia and giving a blue colored solution, and a solution contains here ammoniated electrons, ammoniated cations in them. There's a property regarding solution in the liquid ammonia we have. Then next, now properties, chemical properties, reaction with air now. Alkali metals readily react with air as well as water now. Suppose when you are exposing the alkali metals to air, what will happen is they react with air, and you can take reaction like this. So for example, sodium is there. When exposed to air, it reacts to form sodium oxide, and then this further absorbs moisture of air and dissolves in that, forming sodium hydroxide, and this may absorb even carbon dioxide of atmosphere also, and then it forms Na2CO3. Na2CO3. It implies that when sodium is exposed to air, finally we are going to get sodium carbonate, and therefore the metals are not stable when exposed to air now. Hence they are stored in inert solvents, something like kerosene and then paraffin wax. So they react when exposed to air, and finally you are going to get their carbonates here. Therefore, they are stored in inert solvents. They are stored in inert. This is the reaction happening when exposed to air now. Now, when they are heated in air now, reaction is different. Lithium preferably forms lithium monoxide, and sodium forms mainly sodium peroxide, and potassium forms mainly potassium superoxide. These are the main compounds formed by lithium, sodium, potassium when they are heated in air now. We observe that down the group, the formation of higher oxides is gradually increasing because increasing in the stability due to the lattice enthalpy. So down the group, we can say that lattice enthalpies of higher oxides is increasing. Therefore, down the group elements are forming higher oxides now. And peroxides are diamagnetic in nature, while superoxides are paramagnetic. Means superoxides are paramagnetic in nature, means superoxides are going to have unpaired electron in them. Therefore, superoxides are paramagnetic in nature. Second group elements do not form superoxides. Means second group elements, they can form only oxides and peroxides but not superoxides. That's regarding the oxide formation of these elements. Then comes reaction with water. The reaction with water, reactivity is increasing down the group. That is because of increasing in the electropositivity of these elements now. Lithium reacts slowly with the water and liberates lithium hydroxide, forms lithium hydroxide and liberates H2 gas. Sodium reacts similarly, but reaction is going to be a fast reaction. Compounds will be similar in nature. Potassium, similar reaction, but reaction is going to be very much violent. So the reactivity is increasing down the group because of increasing in the electropositivity. When it comes to second group elements, the first element beryllium will not react with water, whereas the rest of the elements are reacting with water. So in first group elements, all react with water. Second group elements, except beryllium, rest of the things will be reacting with water. Then comes halides now. In the case of halides, means the all halides have higher heat of formation. Means suppose when you take here sodium plus X2 giving rise to say NaX, that is to say here 2 and 2 regarding formation of sodium halide. So delta H value itself is called heat of formation here now. 1 mole of is being for heat of formation. All halides are having higher heat of formation. They have higher heat of formation. And then for a given metal, heat of formation is decreasing from fluoride to iodide. For a given metal, heat of formation decreases from fluoride to iodide. That is because for a given metal, iodide is more covalent. Iodide has more covalent character. Iodide has more covalent character, therefore its heat of formation is less now. Then when it comes to the lattice energy of these compounds, lattice energy is energy liberated when 1 mole of ionic crystal is being formed. When 1 mole of ionic crystal is being formed. And lattice energy mainly depends upon the Coulombic force of attraction. Depends mainly upon the Coulombic force of attraction. And therefore, lattice enthalpy will be increasing with the increase in the size of lattice enthalpy. Lattice enthalpy decreases with the increasing in the size of the cation, because Coulombic force of attraction depends upon the size and depends upon the size as well as distance between the ions. So lattice enthalpy is mainly energy given when 1 mole of ionic crystal is being formed. For example, Na plus Cl minus given as to NaCl, the energy formed itself is called lattice enthalpy. Is mainly depending upon the Coulombic force of attraction, and therefore when the size increases, size of the cation increases, Coulombic force of attraction decreases, hence lattice enthalpy also decreases. So this is the decreasing order of lattice energy of these fluorides given to us. The next point. Regarding halides, there is one key point to understand. That is, means we have to know 3 main points: lattice enthalpy, melting points, heat of formation. These 3 points in the case of halides. Let us take an example like this. Say lithium halide means lithium chloride, then sodium chloride, then potassium chloride, then rubidium chloride, Then comes cesium chloride we have. We have taken all chlorides, lithium chloride, sodium chloride, potassium chloride, rubidium chloride and cesium chloride here. First one, the element which is the compound which has highest lattice enthalpy. Lattice enthalpy depends upon Coulombic force of attraction. So the smaller the size of the cation, higher the lattice enthalpy. Therefore, this element LiCl is going to have higher lattice enthalpy, higher lattice energy. Higher lattice energy. So means last is going to have lesser lattice energy than now. Then comes regarding melting points. Melting points for when the compound is having higher lattice enthalpy, melting point must be also higher. But lithium compounds have slight covalent character in them. Therefore, lithium compounds are not having higher melting points. So all sodium compounds have higher melting points. Therefore, now NaCl is having high melting point. High melting point. That is to say, LiCl is having lesser melting point than now. When it comes to high heat of formation, the more ionic character leads to high heat of formation, and this is having higher heat of formation there now. So the compound has high heat of formation. So therefore, high heat of formation is cesium chloride, high lattice enthalpy lithium chloride, high melting point sodium chloride. So this is also having high, even ionic nature also higher for this, is a high ionic nature, is having more ionic nature also. Implies it is going to have more covalent nature than now. So more covalent nature. More covalent nature. So these are the now 3 points to understand: lattice enthalpy, melting points, and then heat of formation. So melting points are exceptional because though melting points depends upon the force of attractions, since lithium compounds are having covalent character in them, they are not having higher melting points. Sodium compounds are going to have higher melting points. This is regarding halides properties. And then coming towards second group. In second group elements, except beryllium halides, remaining all other halides are ionic in nature. In first group, lithium compounds have covalent character. Second group, beryllium compounds are completely covalent in nature. For example, when you take beryllium halides have different structures, especially beryllium chloride. If you are observing, beryllium chloride has different type of structures, BeCl2. When you take BeCl2, say in vapor phase, if it is above 1200 Kelvin, vapor phase and then above 1200 Kelvin, the molecule exists as a monomer, means it will be like this. So beryllium chloride, that is above 1200, it will be in vapor phase now. Vapor phase it has. If it is below 1200 in vapor phase, it exists as a dimer molecule. Means 1200, it should be 1200 Kelvin, but it should be below. It is below this one, it exists as a dimeric structure. So that is to say, the structure comes like this. So beryllium, another atom of beryllium here. So Cl, 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 Cl. So like this we have, this way we have, this is going to be a coordinate covalent bond from these two. Like this we have. That is, everything is a dimeric structure, BeCl2. And if you take solid form, if you take the molecule in solid phase, there is going to be a polymeric structure. It has a polymeric structure. So beryllium, it is a polymer. So few number of atoms you are taking here, Cl, Cl. So on and so forth we have. So these two I am putting normal covalent bonds like this, and other one will be a coordinate covalent bond in this way. And so on and so forth we have. It's a polymeric type of structure. So beryllium halides are covalent in nature. They have different type of structures, especially BeCl2. In vapor phase above 1200 Kelvin, a simple monomeric structure. Below that, it is going to be a dimeric structure. Solid state, the molecule is existing as a polymeric structure it has. This is regarding halides. Then comes oxides and then hydroxides. First group, oxides as well as hydroxides, all are basic in nature and basic property further increases down the group. When it comes to second group elements, beryllium oxide, beryllium hydroxide, the first one, are amphoteric in nature, whereas remaining all of them are basic in nature and basic property further increases. So in S block elements, among oxides and hydroxides, only beryllium compounds, beryllium oxide, beryllium hydroxide are amphoteric. Rest all oxides and hydroxides, all of them are coming under basic nature, and basic nature further increases down the group. Then comes carbonates and bicarbonates. First and second group elements form solid bicarbonates. First as well as second form solid bicarbonates. And in first group, lithium carbonate is unstable, and whereas other carbonates are thermally stable. That's to say, when you take lithium carbonate, means Li2CO3 dissociates very easily to give Li2O and then CO2. But when you take Na2CO3, this thermally will not dissociate. Means thermally stable compound we have. So only lithium carbonate is unstable in first group elements. Rest of that thermally stable compounds. Now when you take second group carbonates, all of them dissociate, but the stability will be increasing. Suppose when you take calcium carbonate, giving rise to calcium oxide plus CO2. Take barium carbonate, BaCO3, also dissociates, use BaO and CO2. Means in second group, all of them dissociate upon heating, but dissociation temperatures will be increasing. That implies that stabilities are gradually increasing there now. So in first group, only lithium carbonate will dissociate, rest will not dissociate, rest will not decompose. Whereas in second group, all carbonates start decomposing there now. Then when it comes to bicarbonates now. So if you take bicarbonates, first group elements form bicarbonates, whereas second group elements form bicarbonates only in their aqueous solutions. Means first group elements form solid bicarbonates we have. Second group bicarbonates exist only in their aqueous solutions. When it comes to stabilities of these compounds, stabilities are increasing down the group. So all bicarbonates of first group decompose on heating, but stability gradually increases down the group. Means if you take, for example, sodium bicarbonate, giving rise to, it dissociates to form Na2CO3 plus CO2 plus H2O. So it dissociates now. Similarly, you can take potassium bicarbonates also. This compound also dissociates, K2CO3 plus CO2 plus H2O. Means all of them dissociate upon heating, but stability will be increasing down the group. Means potassium is much more stable when compared to sodium. That is the order of stabilities of bicarbonates we have. Then comes diagonal relationship. Diagonal relationship means here diagonally lithium and then magnesium, beryllium aluminum, boron silicon have similar type of properties, and that is because they have similar electronegative values. Now let us take some examples with the properties, some examples here for diagonal relationship properties. Both lithium and magnesium decompose slowly, water liberating H2 gas. So both are reacting with water and liberate H2 gas. Both form nitrides, lithium nitride and magnesium nitride. Both form oxides, normal oxide, lithium oxide, magnesium oxide. Both metal hydroxides are weak bases, and they are slightly soluble in water. So lithium and magnesium decompose water, both form nitrates, both form oxides, both metal hydroxides are weakly basic in nature, they are slightly soluble. And then both metal carbonates will decompose on heating to give a carbon dioxide as well as metal oxides. The carbonates, phosphates, fluorides of both the elements are insoluble in water. This is important thing now. Carbonates, phosphates, fluorides. These elements are insoluble in water. LiCl and MgCl2 both are deliquescent. They form covalent solids only because of high polarizing power, and they hydrolyze to form respective hydroxides. And the nitrates of lithium and magnesium, they easily decompose to form metal oxide and nitrogen dioxide. It is something like carbonates of this decompose to form metal oxide and carbon dioxide. Similarly, nitrates also decompose and then form the oxides as well as the nitrogen dioxide. Means you take a reaction like this. So lithium nitrate on decomposition, it forms lithium oxide plus nitrogen dioxide. Similarly, you can take magnesium nitrate also, you can take here. Also dissociates to form magnesium oxide plus nitrogen dioxide. So compounds are oxides as well as nitrogen dioxides we have. This is regarding nitrates we have. Then comes solubilities now. Solubilities of these metal salts, if you take solubilities of the metal salts of larger anions, they are decreasing down the group. Means, for example, when you take sulfates, let us take sulfates. So beryllium sulfate, then comes magnesium sulfate, so on and so forth. Let us take barium sulfate. The sulfates, when you consider here, the sulfate solubilities are decreasing down the group. Means first is more soluble, last is less soluble. This is going to be the order of solubility in them. When it comes to solubilities of salts containing smaller anions, for example, when you take, say, beryllium hydroxide, magnesium hydroxide, and so on and so forth, take, say, barium hydroxide, the solubilities of these compounds are increasing down the group. Means the order comes like this. They are increasing down the group we have. This is the order of solubilities of the salts having larger anions and salts having the smaller anions we have. And commercially important compounds of group 1 and group 2. Sodium carbonate NH2O is called washing soda, and this is bicarbonate used in the baking soda. CaO is called quicklime, and calcium sulfate 2H2O gypsum, and half H2O is called plaster of Paris. Sodium, potassium, magnesium, calcium have biological importances also.